Good morning students, welcome to the session 2 of numerical analysis. So in this session let us study about the problems on errors. In the last session we have studied the definition of errors and types of errors. So we have studied some examples also in previous session. Today let us take some more examples on errors. Let us take first example. The absolute error of the number x is equals to 147.1946 is 0.15. Find out how many digits of x are valid and round off the number x retaining only valid digits. So here first you have to make the make sure that what are given in this. Here the number is given and its absolute error is given here. This 0.15 is the absolute error. So what is given here? So given absolute error here, absolute error is equals to, absolute error we know here EA, it is equals to given here as 0.15. And by the definition of absolute error here, so we know that absolute error is always less than or equals to 1 by 2 into 10 raised to m minus n minus 1. Take this one as equation number 1. So here x is 147.1946. We can express this one in valid significant figures like this here. This is 1 into 10 raised to 2 plus 4 into 10 raised to 1 plus 7 into 10 raised to 0 and etc. It is like this. So that is we know x is equals to alpha 1 into 10 raised to m plus alpha 2 10 raised to m minus 2 etc. So here comparing these two we'll get here m is equals to 2. So now this equation 1 implies here. This equation 1 implies absolute error here is given is 0.15 which is less than or equals to 1 by 2 into 10 raised to m. Here m is 2 because from this we can see here m is equals to 2. 2 minus n minus 1. After simplification we will get here 2 minus into minus plus 1 is 3. 3 minus n. So 0.15 is less than or equals to 0.5 into 10 raised to 3 minus n. So you have to verify here, you have to verify for what value of n this inequality satisfies. That value you have to take here. So first start with n is equals to 1. So when you take n is equals to 1, so then it becomes what here? 0.15 less than 0.5 into 10 raised to 3 minus 1. In place of n, you put 1. So 3 minus 1 is 2. So 0.15 is definitely less than 0.5 into 10 raised to 2. So 0.5 into 10 raised to 2 is how much here? 10 raised to 2 means 100. 100 into 0.5 is 50. So this inequality satisfies. So this inequality satisfies for n is equals to 1. Similarly, put n is equals to 2. Then what happens? It is 3 minus 2 is 1. 0.5 into 10 is 5. So this also satisfies here. 0.15 is definitely less than 5. So second condition, that is n equals to 2 is also satisfied. Next you have to verify it for n equals to 3. So 3 minus 3 becomes 0. 10 raised to 0 is 1. So 0.5 into 1 is 0.5. So definitely here 0.15 is less than 0.5. It is also true. So the value of n is equals to 3 is also satisfied this equation. And but when n is equals to 4, then see what happens. So it becomes 0.15 which is less than 0.5 10 raised to minus 1. 10 raised to minus 1 means divided by 10. 0.5 divided by 10 is 0.05. So this inequality does not satisfy because here we know 0.15 is always, which is what here? Which is always greater than. This is greater than 0.05. So our inequality does not satisfy the condition when n is equals to 4. Therefore only up to 3 digits are valid digit and the next digits are not valid. So therefore here this implies n is equals to 3. Thus 3 digits are valid and in this number you will take only 3 digits here. So this implies here x is equals to 147 and the remaining digits are not valid. We can neglect the remaining digits. So this implies here x is equals to 147 and it has only 3 valid significant digits. Let us take one more example. Find the relative error in the number 13.74 if all its digits are valid. Means here it has how many digits? 4 digits. All 4 digits are valid, means n is equals to 4 here. So you have to find the relative error in this number. So here the given number x is 13.74. Since all the digits are valid, therefore n is equals to here 4. Now we have to express this 13.74 in valid significant figure. That is, here we know x is equals to alpha 1 10 raised to m plus alpha 2 10 raised to m minus 2, etc. This is the general form here, 10 raised to m minus 1 it is. Now we can express this x is how much here? This is 13.74 is equals to 1 into 10 raised to 1 plus 3 into 10 raised to 0 plus 7 into 10 raised to minus 1 plus 4 into 10 raised to minus 2. So now comparing these two here, we can have here alpha 1 is equals to 1 and m is equals to 1. And we know in the previous session we studied this definition. Relative error is approximately equals to 0.5 divided by alpha 1 into 10 raised to n minus 1. This relation we studied in the previous session. So here let us substitute the values alpha 1 and n here. So it is equals to 0.5 divided by 1 into 10 raised to 4 minus 1. That is 0.5 divided by 10 raised to 3. So it is equals to, if you take in the numerator, it becomes minus. So relative error is approximately equals to 0.5 10 raised to minus 3. So 10 raised to minus 3 means you have to take the decimal point on the left side 3 places from this decimal point. So it is 1, 2, 3 it is. So 0.0005. This is the relative error of this number which has 4 digits are significant. Let us take one more example. How many decimal digits must be taken in the value of under root of 180 for the error not to exceed 0.1%? So here first you take the approximate number of this one and then you have to find the error which does not exceed 0.1%. Let us take here the given number as x is equals to under root of 180. This is equals to 13.4164 This you have to find using calculator. So it is approximately like this. Now we know percentage error is given here. Percentage error is given what here? It is not exceed means it is less than or equals to 0.1. So now we know percentage error is equals to relative error into 100. This we know in this from previous session. So percentage error is relative error into 100, which is less than or equals to 0.1. So this implies relative error is equals to, take 100 in this side, it becomes 0.1 divided by 100. Take this one as equation number 1. So now but we know that here relative error, this is again the definition of relative error, which is approximately equals to 0.5 divided by alpha 1 10 raised to n minus 1. So which is equals to 0.5 divided by alpha 1. Alpha 1 is in this number. You have to take this one as here alpha 1. We know this can be written as here. This is equals to alpha 1 into 10 raised to m plus alpha 2 into 10 raised to m minus 1 plus etc. So first digit is alpha 1 here, that is 1. So 1 into 10 raised to n minus 1. Because here we don't know the value of n, you have to keep this one as it is. So but here relative error here is 0.1 divided by 100. So you have to substitute that here. So relative error is 0.1 divided by 100 and it is equals to 0.5 divided by 1 into 10 raised to n minus 1. So this is what here, this is relative error is 0.1 divided by this one. So 0.5 divided by 10 raised to n minus 1, which is less than or equals to 0.1 divided by 100. 0.1 divided by 100 gives what here? 0.001. So which is less than or equals to 0.001. This implies here, take a cross multiplication of this one. 0.5 is less than or equals to 0.001 into 10 raised to n minus 1. So it is equals to 0.5 divided by, take this 0.001 here, which is less than 10 raised to n minus 1 can be taken as here 10 raised to n into 10 raised to minus 1. This we know. So that is here a raised to m plus n is nothing but here a raised to m into a raised to n. Here it is minus, so it becomes minus here. So it is equals to, this is equals to, we can take here this one as here 5 divided by 0.5 means it is 5 by 10, isn't it? So 0.5 means it is 5 by 10. We know this. 0.5 is nothing but here, 0.5 is nothing but here, 0.5 we can take here 1 in the decimal place and number of zeros after this one decimal point is 0, so it is 5 by 10. This is 5 by 10. and 1 by 0.001 means it is 1 by 1000 it is. If you take in the numerator it becomes 1000 here. It is 1 divided by 10 raised to minus 3. So it becomes here, if you take in numerator it becomes 10 raised to 3. So it is 1000 it is, which is less than or equals to 10 raised to n into 10 raised to minus 1 is 1 by 10. So this is 5 into 10 raised to 3, which is less than or equals to 10 raised to n. Here we can cross multiply here. So it is this 10 get cancelled. This 10 and this 10 get cancelled. It becomes like this here. So this implies here what here? This implies again. So as you have done in previous example, again you have to verify here for n is equals to 1. If n is equals to 1, this inequality does not satisfy. But that is here 5 into 10 raised to 3 means it is 5000 it is. So 5000 is less than 10 is wrong. If you take n equals to 2, it is 5000 is less than 100, it is also wrong. If you take n is equals to 3, it is 1000. So 5000 is less than 1000, it is also wrong. So if you take n equals to 4, that is 10,000. So 5000 is less than 10,000 is correct. If you take n equals to 5, it becomes here 1 lakh, which is again it satisfies this condition. 5000 is less than 1 lakh, etc. If you take n value more than 3, then all the values which are greater than 4 satisfy this condition. So this implies here n is greater than or equals to 4. Hence at least 4 valid digits must be taken here. Minimum 4 valid digits you have to take here, and remaining digits are we can neglect. So therefore here you have to take only 4 valid significant digits in this example.